I started on 9, so I thought 9 was the one to do today. 9's the one to do. But for 9, where do we just Google the like conductivity and the permittivity of the objects of the material to use for the equation? You know what I mean?
Which number is that?
And like the 9.9 and like the refraction. Well, I guess we have to ask them. You know what I mean?
What did I ask? You're using the right book, right?
Yeah. I think so.
The real electric and magnetic fields from monochronic plane wave. 9.9.
Oh, 9.19. If there's a point where like you end up with, I guess you get the electric permittivity.
Oh yeah. Oh yeah, you can.
Oh, okay.
Yeah. You can, if you type them into Wolfram.
I'm working on it. Yeah.
Criminal.
I'm a little behind. I know.
Oh my god.
Except the difference.
You're so excited for the fact that I'm going to Tokyo. You're like, oh, I won't even have to think that week. Just turkey only.
Yes.
Where's sense?
I do this.
Oh, yeah, I'm
Just trying to get the whole screen in here. Okay, good.
This is probably really fun.
Are you guys ready?
Yeah.
Yep. What were we talking about? We were
In that.
skin depth. No one liked that term, but unfortunately, that is the correct term. What does it mean? Exactly. Right. So any type of light can penetrate, and you know, one of the questions you ask is what type of light. So it's very important to think that just because we see in the visible does not mean that we are not surrounded by other forms of light. Right? So a butterfly in this room will feel things differently than a snake. Right? Snakes can see in the infrared, butterflies can see in the ultraviolet. Okay. We're going to get into a little bit more about those properties of light in a second. We're thinking just about the most important question, the one that you've been thinking about all week, which is how for come, why, phone not work, and tunnel. Right? Elevator, maybe? You want elevator or you want tunnel?
I like elevator.
Did you do the experiment?
That's one.
Oh, we didn't do the.
Did anyone do the experiment in the elevator here?
Nah.
I didn't try this elevator, but I've been in the elevator on a phone call.
I live on the 3rd floor, so I'm lazy and just take the elevator. And every time I go in, it's like,
See? Okay, yeah.
is that how Faraday cages work?
Well, not get ahead of ourselves. We don't know anything about a Faraday cage yet. Okay. So let's write what we had last time. Okay. And I told you that we were going to look at 2 specific cases. So we had this thing, then we had K, and now our K has 2 components. So I've added this little twiddle to signify that it's complex. And it was disgusting looking. It looks like this. Right? And then you get it to something that looks like this. So now we have a K and kappa. Is that good or you want a different one? Please, no one cares. Okay.
Cursive K?
Like that?
Yeah, that's good.
I don't think my cursive K will look any better, but. Cool, super intuitive, right? Not intuitive at all. But we can break these down. We saw that the first one, when we're thinking about what this means, right? This one here was the wavelength of the wave. And then this one here talked about the penetration, right? Because when we use K inside of a complex exponential, that imaginary part that this kappa is associated with then hits that other I, so there's an I times an I, and this becomes a minus exponential. And this is associated with your skin depth, right? K and Z, the penetration depth, are related, one over the other. That make sense? Okay. We saw the special case. So when sigma was much, much less than omega epsilon, what was that? Very low conductivity, good. Yeah, I didn't edit that one.
It was more simplified, like Z naught.
Yeah, but what does it mean? Low conductivity had an unusual result, something that we didn't expect.
Oh, it had low skin depth, skin. It was higher skin depth. I thought it was low skin depth.
All right, fight, go ahead.
That they travel further in the material.
Travel further in the material. Okay, that's very weird. Let's look at the other one and we'll see, we'll do the math, right? We'll see if that's right. So let's imagine a very good conductor, okay? So this one, small conductivity equals question mark. Let's do the other one. Let's do sigma is much, much larger than omega epsilon. I know that looks like weird, but it's not. Okay. So if sigma is much bigger than omega epsilon, sorry, flip that here. I don't think people care. They care. Flip that. All right, sigma is larger than I, okay? So sigma over I is a big or a small number? Big number. Okay, so sigma over I is a big number, right? Okay. So you can add or subtract 1 to a large number with little effect, right? Because this is a big number, and then I'm gonna square it. So it's bigger square, right? And so that's basically 1. And then I can take a square root, so that's basically the same number, right? And then I subtract 1. So it's basically this number, right? Okay, so these are very intense mathematical arguments, right? So in this circumstance, you get something like K equals, or sorry, kappa equals omega. I'm gonna put all this garbage in front, mu over 2. But now this is just gonna look like sigma over I minus 1. Square root. Right? And I just said this is a big number, so let's do it again. So this is omega square root of epsilon mu over 2 times sigma over epsilon mu. Sorry. Yes. What's that equal?
Omega times the square root of sigma over two.
What's that?
Omega times the square root of sigma over two.
Yeah, we can bring it in too. So this becomes omega squared in there. This one disappears, this one disappears. One of these disappears for one of this. Right? So we get this little fun thing. Mu omega sigma over 2. Okay. Turns out that's the same result for K. So what does that mean? Skin depth. Let's see, skin depth was Z naught or something, right? And it was proportional to what?
1 over K.
1 over K. Okay. So then skin depth here will be
Very small.
very small, right? So let's flip these over. 2 over mu naught omega sigma. And what was the argument at the beginning of this?
Sigma's big.
Sigma's big. So whenever a big number is a small number. Okay, does that make sense? Let's take a piece of copper and let's try to shoot some light into it. What happens to those waves?
They just, they still lose their energy, or they quickly lose their.
Quickly lose their energy, right? And maybe not energy, we don't know anything about the pointing vector, but that idea is 100% correct. Those waves dissipate very quickly. And we know in our mind, we say, oh, well, that's because any charge that's, inside of a conductor is put onto the surface very quickly. We saw that the distribution of free charge in a conductor, rho of F, also goes with an exponential. So this is not very surprising to us, right?
How did omega not second cancel omega inside?
Well, so this becomes omega squared inside. And then one version of it disappears.
Oh, so it's a new omega inside. Oh,
Yeah, I just added that after the fact.
Oh.
There you go. Let's do it like this. Is that better?
yeah.
Sorry. Sometimes I do like 4 steps of math instead of just one at a time. This is also why I used to turn in really bad homework. So this is why I'm much more lenient about homework than people realize. Horrible. Yeah, I turn in like the worst homeworks. People are like, you don't understand anything. Yes, I do. Just didn't write it good. Okay. Okay. So has that explained all of our does this describe why we can't have a phone in an elevator?
Maybe I was doing Wi-Fi calling.
Connecting to Wi-Fi. So interestingly enough, right, we have to think about how the hell do our phones work, right? So my mom's calling, right? And so what's happening?
Sending a signal going back.
What does that mean? What signal?
Frequency, a radio wave.
Ah, a radio wave, perhaps? Okay. So is it radio waves?
Probably.
You definitely can't see the waves, so.
You can't see the waves, so I can't tell how big they are. Right? Okay, so it's not radio waves.
Satellite
What's that?
satellite stuff. I'm not sure. I'm not an expert at satellites, but I know there's like cell towers.
What kind of waves?
What kind of waves do phones make?
Yeah, that's perfectly fine.
Cell phone waves.
Okay, cellphonewaves.tm, not a brand.
Okay.
Okay, so in physics, we do learn how the world works.
Yeah.
Okay, so you are seeing currently my body with a visible light. More intense light, right? Ultraviolet light. So you see this like concert in, or was it South Korea? And they wanted to put black lights everywhere. But instead of putting black lights everywhere, because I guess they couldn't afford the black light, they just put those UV disinfecting lights. Now, everyone who has understood what UV is knows that if you dance under UV disinfecting lights for 4 hours, you will go blind and your skin will start to be very tan. So all of them reported this giant problem, right? Because rather than using visible light that's purple, they used ultraviolet lamps. Okay. So this is a form of light that we can see the tail end of, right? And we're like, oh, it's dangerous. We should stay away from it, right? Okay. Infrared light, we're familiar with this. We put on our goggles in Call of Duty 3 and whatever. I don't know which Call of Duty y'all are on. But everyone's familiar with that, you know, the videos, right? Okay. So then you kind of go outside of the realm of what you're comfortable with. And, you know, I asked you this question, how does a phone work? So which direction is the light? Is it more intense than UV or is it less intense than infrared?
And both less intense as it could us.
Yes, there you go. Okay, so maybe you have parents, my mom was like this, she was like, you know, you can't get too close to cell towers or they're gonna like fry your brain.
This one, my grandma said about microwaves.
Yes, okay, my mom said the same thing. Microwaves are unhealthy, they're gonna fry your food. Or they're gonna fry, you're gonna give you cancer.
She was
And
telling me
that's-
not to put my head by it.
Yeah, right, very dangerous, right? Is it?
No.
No, and we're gonna demonstrate that today. Okay,
And
So-
don't put yourself in it.
no, you're right.
Yeah, it's good for
Yeah,
your body.
don't chop off your arm and put it in, right? That wouldn't be good. Okay, but the real question is here is what is doing the transmittance of information? So I said it wasn't radio waves. Maybe that's wrong to say because radio waves spans a really large amount of light, right? Anything that gets over a certain amount, we basically just call it radio waves because we've given up. But in fact, it's the shorter wave part of radio waves, something we call microwaves. Okay. So in fact, everything that is Bluetooth technology, everything that is working from the cell phone generator is in the microwave region. You think to yourself, well, why isn't it cooking my brain? No. Okay, well, one, because it's not that energetic as the microwaves that are inside of your microwave. And two, there's not enough by a lot. Right? Okay. So let's find out. So let me ask you this question. Let's say we have 3 centimeter. Okay. 3 centimeter microwave. Okay, they're gonna be incident on copper. I think Cu is copper, right?
Yeah.
Oh, yeah.
It's right there.
I can't read. Okay. So let's say sigma for copper is 5.8 times 10 to the 7. Whatever that's called. And let's do it like this. The permissivity is like that. Okay. For yourself, please find out what the skin depth is.
Wait, I can't.
You won't even necessarily need to get that. What do you have? Great. What about you?
No, it's you.
Here's the constant.
Well, it's the constant specifically copper.
Oh, that's good.
What's you?
Permittivity is.
No, not like, or did it? I think so too.
Are you relying on the fact that it's 2 over bingo?
Yeah, I'm gonna just use the relationship between C and.
Yeah.
I don't have.
Can we just make it 1?
I can't quote it. But what is,
Don't have.
I heard that.
so C squared equals 1 over mu epsilon, right?
Yeah.
That's right.
But you might end up with something that has C in it. And so therefore you might end up with something that is related to what I have.
Okay, okay.
You have a lot. Okay.
I heard that's.
No, I don't.
I mean, it's basic money, it's what I want.
3 cm.
What?
What's the 3 cm?
I don't know.
Did I get
What is it?
Is this?
What is the length? Oh, interesting. So this is a 3 cm microwave. But what am I describing with the 3 cm?
The wavelength.
The wavelength. Right? So interestingly enough, I only ever have to tell you one of the two properties. So I can give you 2 gigahertz microwaves, or I can tell you that they're 5 centimeters. But because one infers the other, right, you can always say, oh, whatever is more convenient. So gigahertz is like 10 to the 9 hertz. That's not a fun number in the calculator. 3 centimeters, easy, right? Okay. Don't worry, we'll do gigahertz.
Let's see if
Oh,
it's,
great.
Megahertz, not megahertz.
Yeah.
okay.
If and when you get an answer, do not shout it out.
Great.
Oh, also, if you need me or not, permittivity of free space in the frame book. If you ever get, like, say for an exam next week.
Okay.
Cool.
What is the unit?
I'm not sure.
Figure that out, please. If it's the unit that I think it is, it's close, but if it's not the unit that I think it is, it's very far. Wavelength is not either line. Lengths are in what type of units? Meters, centimeters, whatever they are, right?
And then, the conductivity is omega times meters. Or. Is that
Ohm meters.
ohm meters? Oh, that's ohm meters. Okay.
Makes sense.
Is that 1/ohm meters or just ohm meters?
No, sorry, that's,
It looks like 1/.
Yes.
Sorry.
yeah, that's just like trying to tell you the units here.
Oh, okay.
Not ohm meters.
Alright.
Is that true? Conductivity
I think it's inverse.
is inverse. Conductivity is ohm meters, yeah, that's. No, I think it is.
Okay. I was like-
Let's leave it like this. Oh, shit. Let's leave it the way it was written.
Okay.
Units.
There's the conventional name for that. And then there's also like what it used to be called, which is just like ohms backward. Mo.
Yeah, if you want it in its, well, what's the number that you have? Put that in the context of him and them. How many meters is that? Is that more than one?
Yeah,
Is it a lot more than one?
yeah,
Okay, is that 10,000? More than 10,000 meters.
yeah.
And what did we claim for a good conductor would have?
So, so we're doing that.
Right. Because when signal is much larger, the claim was the skin depth would be small.
So I switch from.
Your skin depth is very low.
No, I don't.
let's switch
I have a
from
one over that.
this.
I did K.
Was that K?
That was K.
Oh, okay, well, now tell me what the skin depth is.
Oh.
I prefer it, yes.
John, you're putting it in the chat, right?
What's that?
Put the skin depth in the chat. There you go.
The skin depth? Oh, you mean like the final answer? I'm still working on it.
Units, and that's much closer. Yeah, K does not have units of meters.
Oh.
K is a wave number, which is by definition 1 over meters.
Okay.
I should say 1 over. What do we get?
I thought I had it right, but I don't think it is anymore, but I had 0.32. But then my units,
0.32 what?
that's where I realized I messed up that. Something
You said we could do more ahead without a calculator.
needed for ohms. Well,
No, I said it might not be
because
You can use,
What
you know,
is it?
just do order of magnitude numbers.
Oh.
Like this is 10 to the 12, and this is basically 10 to the 8,
I plugged in for
Right?
like this.
and then it's just significant by adding.
U would be 1 over c squared e. So it's, but there's already one e up there. Oh, there it is. Okay, you know what? I get it.
All right, what votes do we have here?
Oh, I did it. Oh, no, I can do it.
I ended up with like a V term, like a square root, 1 over the square root of V. I don't know if anyone else ran into that.
1 of the square root of E?
V. Like it's in my answer and I don't know what that's about.
Is your V omega or what is your V?
I replaced omega with like the relationship that it's like omega equals V times K.
Okay. So what would the V there be?
I think.
Wait, what? Sorry.
What would the V there be?
I mean, can we just say it's C?
Yeah, it's light, right?
Oh, okay, sick. Okay, cool.
Every type of light.
Oh, perfect.
C,
Okay.
right? So this microwaves move at C, okay? C equals C. Always. And the point of what we're doing here, right? So this, obviously, these waves come in, they hit the medium. I'm not giving you an index of refraction of where they're coming from, nor am I giving you an index of refraction of what they are inside. So to first order, we're just figuring out how they would propagate. Does that make sense?
Okay. Then give me a second. I might actually have it. Sorry.
All right, anyone else have it?
I haven't answered these wrong.
I'm gonna check in the units before I say what I think it is.
Who's got it?
Do we use that equation on the board there or no?
Which one? This one?
Yeah,
Well, you have to tell me. For this one, what are you using?
I tried that,
Yes, and why would you want to try that?
because the thing was big,
Because the connectivity big, right?
but I
That's
got,
big connectivity.
I got meters per ohm,
Okay.
so.
Um,
Unless the epsilon has units, I googled it, it was like farads per meter.
yeah, the epsilon definitely has units. So
Okay.
what you can do here is if you just ignore that, right? The combination that you're gonna get out will be in meters because you've only used meters. You see why that is? So here's a here's a length, L. Okay? This combination here and here, this has units of ohms. This has units of per ohms. And the M's is what you end up with.
So it is just meter?
It should be just meters.
Oh, okay.
I got
Okay.
5.57 times 10 to the negative 7.
5.57 times 10 to the negative 7 meters.
Hopefully meters.
I got 0.32 meters.
Point what?
32 meters?
I,
3,
it was.
oh, 0.32
Yeah.
well, probably,
meters? What else did anyone get?
I got those,
I got
and I just,
Anything else? No one else did it?
it's just.
I got stuck on one thing, but I think I just figured it out.
So which of these is right?
I feel like the smaller one would be right because the
These headphones don't go in elevators.
But
because it has
What?
really high
it's so small.
Yeah,
I got 2.22 times 10 to the negative 7,
Okay.
and I'm real sorry.
Mine's like 7 to negative 6, but I'm gonna be trying to.
Isabel's and mine both have the same order of magnitude, so that's why I'm like, maybe we were similar.
Very similar order of magnitudes.
So then.
Yeah,
Right.
No.
gotta be one of those two.
Okay, so I'll give you the answer. This part is right.
Okay.
Oh, wow,
That's what
Damn it, damn it.
Rest of it on your own.
we did,
I know, but you can redo it. Okay, everyone can get the same number. Especially when sitting in front of a Wolfram Alpha that does the conversions for you instead of clocking away on your computer. But this part really matters. Okay, so what does this mean? If I send a 3 centimeter wave, which is how phone towers communicate with phones, okay, and you're in a solid copper elevator, or copper all the way outside, how much copper do you need in order to block? Very little. Maybe thousands of atoms. Right? That's a wickedly small number. Cool.
Is that the idea behind like a Faraday's cage?
Same question that Aaron had actually. No.
Damn it.
Faraday cages exist because a different property that we're not going to talk about here. But essentially, we talked about this in the context of like IMFs, or like, in 2500, 2510. You can build a metal detector to see stuff move through and out. And so you can use those same properties of not wanting to generate waves inside of something that doesn't have anything inside of it. So you ground to the inside, then you can't put stuff through.
Ah. Just kidding.
Let's try radio waves in air. Heat is the worst things ever. What does that do?
probably goes far.
Aha, probably goes far. What is the expectation? The expectation is that it probably goes far away.
Is Arizona very good?
Because air is not a very good conductor, good, so we would use this one over here. Z. Okay,
Let's say, because we communicate with radio waves.
yeah, okay, so one of my favorite things about physics is just like really basic, obvious stuff made very difficult, right? So Newton's first law is like, if I don't press on this, it won't move. Duh, like, don't give him a Nobel Prize for that, that's stupid as shit. So your point is like, well, obviously, we see light go through air, right? And so in fact, you know, I could write this out for you, but I'm gonna show you that the skin depth here, V naught, is 6.6 times 10 to the minus 5. Oh, sorry. Hold on. Yeah.
Really, -5?
Hold on. Yeah. Meters.
Yeah, what does that mean in terms of like it passing through air,
Yeah, it's a very good question.
like the depth of air?
What did skin depth mean again?
How far it goes before it decays by 1%.
Good. How far it
Oh,
goes
okay.
decaying by 1/e. Okay,
It's not like completely gone. It's like-
right. So the amplitude is what's decreasing. Right? So the light itself is not changing in frequency. It's not changing in wavelength, just the amplitude is decreasing. Right, so as it travels through a medium, okay, this stuff can travel 100 times farther than this stuff. Right? That's what that says. Right. Expected farther. Okay. The one thing that is gonna change here, okay, is imagine what would happen if you have like radio waves, you're trying to communicate with the cell tower or something. And you take your cell phone and you go underwater. Are you gonna get good reception? Why? Let's say it still works. Yes.
Oh, that's.
So this is a very interesting point. Water is very conductive. And this is why it's difficult for submarines to be communicated with. Okay. We're gonna double check that number. I'm worried that it's 10 to the 5.
Yeah, that's what I'm trying to right now.
You can work it out here. Here's how my calculation. I'm gonna do 5.
Excuse that. It doesn't.
What?
It's that equation.
That is what we're using.
That's not that.
You plugged in for you.
I had to rearrange some stuff. So I had to give the frequency, not the width. I had to reorganize. Okay.
The ones when we do it through, so I assume that for air is probably 5.
What?
All the ones that I'm finding online are just radio waves through metal, so I assume it's probably, for air is probably 5 on negative.
Okay, good.
But
So,
it would make a negative number with the tens of bottom.
Well, this is gonna match up, right?
Yeah, then it's a minus something.
That's fine. 10 minus 3, square root of 10 minus 5, I think it's 10 minus 6, or 10 minus 5-ish, right?
And then, that's,
Whatever. The point is this relationship. Okay, so on the right hand side, we have the permeability or the ability for waves to go through air compared to those through copper. Okay. We're gonna do one more thing, which is reflection at a conductive surface. And then we're gonna start tying this entire class together. Okay. So let's quickly do reflection.
Yeah, it looks like we're like in the five, I'm saying.
But,
It looks like it's just the five.
okay, hold on.
Where did you get these numbers, the 6.28 and the 12?
That's a long equation.
Yeah, I think that's the one for the 3 centimeter microwave.
Yeah, because
Who you-
that's,
Cause I'm looking at, it approximate the.
equation for
The
long
conductivity.
you can see something outside of the square root.
I'm not sure if this is correct, but they approximate the conductivity of air is zero, and at one first big place to go like, isn't it? Of course, it's not actually,
It's not zero.
so it doesn't go with it,
Yeah.
it can go really, really far, basically.
Yeah, it should go very far.
Yeah.
Right? Not like that.
Yeah.
Incorrect. Bad. Prism. Okay. This is like the notes that you write. So everyone can fuck up. This is why we do it theoretically and then we put it on paper and it's garbage, right? Okay. So let me ask you a question. Okay. We got here's our famous wave. It's coming in. And I think you talked about mirrors earlier this semester, right? What's happening in a mirror? Okay, so now we have reflection at a conductive surface. Okay, so what do we think is gonna happen? Well, you already said reflection for the money, so. Right,
Well, if it can only go so far, then I assume most of it's gonna reflect.
okay, interesting. Interesting. I like that a lot. I'm gonna draw it like this. Is that okay? Okay. That picture makes sense. But our expectation is that the wave's not able to penetrate very far. Right? And so we think that that's gonna force it back on the other side. Let's look at the boundary conditions. So surface charges are allowed on a conductor. So we can do something like mu2, epsilon2, sigma2. And on this side, just mu1, epsilon1, and no conductivity. So insulator out here, conductor here. The boundary conditions look like this. Let's write them. Okay. And similar looking with B. I guess I could have done that there. Sorry. Could have put everything on the left instead of in zero something like that. Fucked it up. Okay, does that make sense? These are the normal boundary conditions. Okay. From this one, okay, we can write, because we know how B and E relate to one another. We can write that one for mu1, V1 I minus E R minus 1 over U2 B2 E. Okay. V in this context here, just not just, you can remember that it's gonna change in each meeting. And, what's that? And I'm putting a, we do this better. Putting a funny little hat on it. Okay. Why am I putting a funny little hat on it?
Because it's both the way on the students.
Right. Together in a very special group way. Right. And so I can also say something like this. EI minus ER. Oops. Beta. ET. You recall when I wrote beta like 2 weeks ago? Beta is like a difference in the connectivities. Or sorry, a difference in the permittivity. Beta is defined like this. Why is omega the same for both? What?
Frequency doesn't change.
Frequency doesn't change at any boundary. By definition, omega has to be the same. Okay. K is going to be written like this. Approximately. Good, I did this right. But we've actually done this before. We wrote it in terms of these coefficients. And we wrote it in terms of 1 plus beta over 1 minus beta or something like that. 1 minus beta over 1 plus beta. The only thing that we're changing here is how we define our k. Because now our k has a complex exponential in it, or it contributes to the complex exponential in the original wave function. So I can say something like this: the reflected wave ER 1 minus beta over 1 plus beta, okay, of the original one. That makes sense. Well, beta was something to do with the properties of the two. I think it had something to do with N1 over N2, if we recall. So we said earlier, you know, if mu1 and mu2 are the same, this is V1 over V2, essentially. So if V2, the speed in here, right? If V2 and over V1 is a big number, say beta is very small. 1 minus a small number over 1 plus a small number is smaller. What about if it's very large? What if beta is really big? Let's look at the other one really quickly. Here's the transmitted wave. Okay. So if beta gets really big, what happens to the reflected or the transmitted wave? That makes sense. What is beta? Beta has something to do with the ratios of the speeds, but now the speed in medium 2 has something to do with the conductivity directly. Right? So this was the idea. Here's K, roughly proportional to the conductivity. If beta gets bigger, K2 has gotten bigger, because omega hasn't changed. Okay, so let's go backwards here. Okay, so big conductivity means big beta. Okay, 2 minus 1, sorry, 2 over 1 plus big number is small number. So large conductivity says, how will your transmitted wave be?
Not too well.
Not well, bad. Okay, let's try this. 1 minus big number.
Could it be
Negative big number. 1 plus big number? Positive. Big number over big number is
negative?
-1. So the reflection is almost complete for big beta.
So that means mirrors are really conductive.
Well, no. It means that if you use a conductive material, you'll get a good mirror. You see the difference? So just because something's a good conductor, right? That means that you're gonna get a very good mirror. But if you use something that's a poor conductor, can also possibly be a good mirror. Right? Being a good mirror does not mean conductive, but good conductivity means good mirror. Water. You put it in a little bowl. Ooh, you stick your face over, Harry Potter style, right? Good conductor leads to good reflective. And that comes out naturally. Weird, right? Okay. Okay. That's everything I want to do for waves. And now we get to do what, in my opinion, is the greatest part of ENF. To do what I'm about to say, so I already told you, right? Like, most of good physics is the dumbest shit you've ever heard, right? It's like, oh, light goes through air. Yeah, I know that. I can see, right? But the fascinating part, right? The reason why people use it as a tool, take yourself back to, you know, the 1500s. You're a peasant working in a field. You got no iPhone, right? You get out there with the hoe, trying to get your like barley into the ground. And some dude like figures out that if you like rub a piece of amber, you like put it over your head, now not my head, but like their head, that their hair will stick up. They're like, oh, that's interesting. And then some other dude somewhere else is like, oh, if I take this little like needle and I put it in water, it like weirdly points to where the North Star is. Isn't that strange, guys? Right? And they're like, oh, that's crazy. And then like hundreds of years go by and they're just like playing around with these little trinkets. They're thinking about like little needles or like spherical balls that somehow they could like charge up. Right? And then they found out there's like these forces of attraction. Oh, it's fucking weird, bro. And they came up with these equations, Maxwell's laws, right? So we saw in this class, right? You took your Maxwell's laws from PK, I think you took it with PK, right? Took Maxwell's PK laws, and that had everything to do with like things being attracted to one another, right? And all of a sudden, you begin to do something that is very unexpected. You begin to be able to describe something that's propagating in a medium that is not like a medium you've ever understood. Because currently we're speaking, you know, I can feel the wind, right? Ooh, awesome. Okay, I can feel that going. You can't feel the E wave, right? You can't like blow the E wave with your hand. You can, yeah, you can. Yeah, it's actually true, but you don't know why yet. Okay, and so interestingly enough, you begin to put these pieces together and you can suddenly make predictions about the properties of light, including forms of light that no one has ever observed before, right? And you say, well, that's just silly. I don't think any of this is true, but we'll let it slide, right? And then you begin to tie this even further. And you begin to ask yourself the question right now, let's say it's the early 1800s. You say, where's light coming from? It's like weird waves that come off. Where do they come from? That's correct. You're pointing to a source of light. But I would argue there's light all around you. So there's light coming from here.
Humans glow.
Yeah, we're glowing. Right? Sun. But where does light come from?
Oh,
From heat.
atoms.
Okay. Take 2 seconds. I want you to think about this really hard. Write down an explanation, okay? Just for yourself. 2-3 sentences. Your best explanation for where light originates. You understand in your head, you have quantum mechanics, you have mechanics. Anyone not taking quantum? Oh, yeah.
Oh, yeah.
You have modern. You know that atoms exist. You know that everything we've talked about so far, you know about capacitors, you know about dipoles. What causes light? And you might say to yourself, oh, it's an electron jumping down. That's not what we're going to learn about. And in fact, that's going to be wrong in the context of how the light itself forms. Quantum mechanical explanation and the electrodynamic explanation, they get married in something called quantum electrodynamics. But you will not have access to that till grad school. Today, we're learning electrodynamics, and there is a specific type of thing that gives rise to electromagnetic waves that we call light. And we're gonna see them. Take 2 minutes, write down your answer. And see how many can guess it.
So we're not allowed to use like the laser example.
No. Lasers don't exist. Not in the 1800s. You have to transport yourself back to a peasant who knows Maxwell's laws.
Oh, okay. Yeah.
Wanda. Don't look at me, that memes.
It's funky.
That's worse.
All right, what do we got, folks? Yeah.
I think that. An atom can sometimes like emit a particle that might be charged. I don't know.
We cannot ever remember. We're ancient. We're people from the 1800s. We don't know about particles.
Stuff.
We don't know about atoms. Yeah.
I said it's from like explosions, like just stuff emitting a lot of energy.
Okay. So like a supernova.
Yeah.
You think that I'm seeing you now by supernovas?
No, like, like just energy, like energy being
Yeah, but where does it come from?
the sun.
No, you can say,
Reflected everywhere.
1800 hasn't been part of the world, like the cameras and stuff.
We are light.
And we are like two, right? So remember what we're saying right now, right? Maxwell's equations, these are not recent formula. Okay? This shit was figured out. And they were like, oh, what? So before Bohr's model of an atom, before Bohr's model of an atomic nucleus, right? Or one orbits the other, we had Maxwell's laws. We knew about the nature of light as a wave. You can talk about the nature of light as a photon later. But in order to do that, we have to understand how light originates at all. That's the purpose of this chapter, which is radiation. Okay? You think in your head, you hear the word radiation, you hear spooky. No, that's not what radiation. We can talk about the definition of radiation. But where does light come from?
Have a bulb in the sun. It's pretty.
You're drawing it all the way back. I'm saying just in this room.
Oh.
How does light come from off of me to you?
All I can think about is heat.
Okay, but we see in the visible.
Yeah.
I don't know what it was.
Okay. So let's define some stuff really quick. Okay, what does radiation mean?
It's kind of.
Yeah, like emission.
Okay, don't use the word emission. And I'm gonna teach you why. Hold on, I'm gonna teach you why. So it's really important that we don't conflate two different types of fields. So when we think about emission, absorption, right, these are absolutely the right way of thinking about it, but we don't want to add that word to the word radiation. The word radiation means for something to give off something to infinity. Okay, so you can imagine that some stuff might be short-lived. So in particular, we can say something like radiation that needs to be accepted at essentially infinity. That whatever is propagating off of me goes off to infinity. And that could be different than emission, because you could have short wave emissions that only go out a little bit and then disappear and die. So we're going to decouple the idea of emission and radiation. Radiation is only stuff that can be received at infinity. Does that make sense?
Okay.
It's a very specific definition. Okay. So they can propagate, say, from a galaxy to us. And nothing happens along the way. Okay. So you have to have a source of radiation, something that creates this propagation in E and B. And let's think really quickly. Okay, here is a charge Q. Okay. What does its E field look like?
It's spreading out everywhere.
Good. And what's its B field look like? Ah, there is none. Secret. And what does its pointing vector look like? Oh, sorry.
And then also,
What's that? Yeah, but why?
because the deep
Ah, okay. So what you have just told me, or what you claim, Kobe, is that charges, stationary charges, cannot emit anything. No radiation of any type. Is that correct? You stand by that?
Wait, how do you, does the pointing vector say what you're reading?
Well, yeah, the pointing vectors, what is the pointing vector again?
It's energy.
The energy flux, right? And so if we wanted something like the power, right? Right, we'd have to take the let's say we have the power as something like that. That would be the power. Okay. And that's still gonna be 0. So Covey in 1865 says a stationary charge puts no power to infinity and therefore has no radiation. All right, who in the village is rioting? No, you're not rioting. Everyone agrees because it's right. So something special has to happen.
Like the particle moving.
The particle, we don't know what a particle is.
The thing is,
What thing?
the thing that's has the E field.
The charge is moving. So it's really important here because if I have a neutron and I just move it, that is a particle. That's the wrong type of particle.
Okay.
So we want to be specific here. I move my Q and suddenly now I get a
Energy force.
energy flux, maybe, right? E cross B. Now I can move it in certain ways such that I don't get E cross B, right? Okay. But this is my goal. I want this to be non-zero. Okay, so a charge at rest makes a constant E field boring. What about a steady current? Like
There is a there's
Okay.
a E field, but it's not changing with time.
B field, but it's not changing time. So B exists. But it doesn't. change. Is that necessary? Get radiation.
I mainly thought about like with the Maxwell law, but if we look at the pointing vector, it doesn't really matter if he's changing time, so. Yeah, I guess it doesn't matter the pointing vector.
Okay, okay. So this is gonna get a little bit more complicated. But it makes a constant V, I agree with that. The charge creates a constant V, the potential. And you can, we can show this in the book, but this also will not radiate. That's really annoying. So I'm gonna state something that we need to not only move the particles, we have to change the current or accelerate. So yeah, those are the same thing. First derivative of current, and the second derivative of the charge. Okay. And then we will be able to produce E and M waves. Okay, so maybe you get E and M waves and you know, they go for a little while and they peter out. Right, they're created just very close to the charges, but they fall off like 1/r². You're like, oh, I fucking.
S wouldn't be zero there, but it's not making waves.
No,
Is that what you're saying, or S would be zero?
So S is not gonna be zero,
Yeah.
but
You need to make waves for it.
the definition of radiation. So the way that we're gonna look at this is something arrives at infinity. And I'm about to show you why in 2 seconds. So you can have something here like E and P. Right? And P is the integral of S dot dA as R goes to infinity. Okay, so let's take an object. Here's my thing. Okay. Let's put a big old circle around. Okay. And this is some distance R. Okay. So let's say I do generate E and B. How does the E and B typically fall off?
That's zero.
Take a single charge. How does E fall off? 1/r². Good. Okay, so that would be 1/r². And let's be generous. Let's say that B does the same thing here. Good, fair or no? So the B fields fall off, right? That would be silly if they didn't. Okay, so let's do that. 1/r². Okay, and what's that times each other? Okay, so this thing is really gonna act a lot like 1/r⁴. Oh shit. 1/r⁴. Okay, so let's look at the power really quickly. For the area of a sphere, what is that? R². Good. Okay, so this has power R², and S has power R⁴. So this power goes like
Whatever.
1/r². And tell me what happens to 1/r² as you get very far away. How small?
Really quick.
Really quickly. Really quickly. Do you get anything in infinity?
No.
No. So you're absolutely right that the pointing vector will carry stuff away, but not very far. Right? If we want this idea of radiation, this current flowing around in a loop, doesn't get us far enough. Oh, I don't want to learn something new, Prismani, right? Okay, so let's figure it out here. We want to look for something that goes like what?
Maybe like something R is in the. Maybe some.
Yeah, there's R's in here, right?
what was
So
it?
if this R, okay, I'll be more specific.
Oh, like R²/R².
Yeah, let's take this and I'm gonna make this an N. Okay.
Thing is two.
So 2, we know that 2 here, if N equals 2, we know no radiation. What about for N equals 3? Even less, worse. Okay, what about N equals 1? Okay, here's the question. Does 1/r equal anything at infinity? How does it asymptote?
It's just
Goes
not
towards
as
zero?
fast.
It doesn't
It
go
adds
all
up
the way.
towards 0.
It doesn't necessarily hit zero, it hits it.
It hits what?
And asymptotically.
Asymptotically?
Yeah.
But does it hit zero asymptotically? Because we're going to infinity.
Like,
Yeah.
they never hit
Yeah.
zero.
Okay, we're gonna have to look at our L'Hopital rule. So what about n equals 0?
Yeah, I know.
N equals 0 would be great, right?
Yeah.
Or even like n equals -1 or -2, is fantastic. In practice, we don't have those outside of the churches. But let's say we did something like this. Okay, so now let's rewrite these ones. And now n has to be the same for both of them. But n is the same for both. Will n equal 2 work here?
No.
No. Will n equal 1 work here? Yeah?
Better, but.
Sure.
What do you mean better?
I say yeah.
It's better.
Well, fight about it. Tell me, is it better or why?
It's better
It's
good.
not our
Cause what,
square.
yeah, cause they, one of ours just went well.
Okay, 1 over r becomes. Okay, 1 over r squared, or r squared is what?
So
That's,
good.
there's no arbitral requirement on that.
1. Another word for that is
One.
Good.
constant.
That could be-
And the integral of a constant at infinity is, or so the limit of a constant at infinity is. It's the constant, right? Nothing's changing, right? Okay, so this is the stuff that can radiate. Oh, okay, so I need to look for shit that looks like that. Right? Where the combination of B and E doesn't fall off faster than 1 over r squared. And that's the only stuff that can radiate. Okay. That makes sense?
Can you say that again?
Yeah, I'll say that 4 more times. Okay, 2 minutes. Okay, 1. If I have something 1 over r squared and I have b 1 over r squared, these fall off too quickly for anything to be able to radiate in the definition that we're using. Radiation being that something from the moving charges or the moving currents will transport energy or momentum or whatever we have to infinity. Okay. So the only combination that we saw that worked because of this r squared dA, right, is something that at minimum, right, has an r squared dependence in S. So if you are smaller than 1 over r squared, right, let's say we're gonna, humor me for a second here. If I have something like r to the 3/2,
there would be like. Square root of r is like the power.
we can do this math, right?
Oh.
Minus 3/2.
Yep.
Is a half, good. So it would go like, right? It would go like r to the 1/2, which is a positive r. Okay. So if you did something like 5/2,
That's more than two.
that's more than 2 now. So now it would go like 1 over r1/2. And I don't really know how that asymptotes, but I'm not happy about it, right? Anytime I got an r on the bottom, I'm probably unhappy. So what I'm looking for here is combinations of E and B where they go like 1 over r. Because I know, at least minimally, if I go like 1 over r, then this goes like 1 over r squared, and then these cancel, and this is a constant. So per my definition of radiation, I need to look for solutions that have a dependence in radius of 1 over r for both E and or B. Okay. Okay. Really briefly, we need to talk about retarded potentials. You heard about these before? Okay. So this is something that you probably need to just familiarize yourself with in the context in chapter 10.3 or something. Electromagnetic waves travel at the speed of light. That's fast, right? Okay. So you may be familiar in astronomy that we're looking at stuff that's very far away and that it takes some time for the light to get us. Okay, but it may have moved. So we are not seeing where it is now, we're seeing where it was. And similarly with everything that we're about to do today, well, I guess not today, next week, we will be required not to use T. Okay, but we'll need to use something called the retarded time. Okay, that's just going to be T, the time that you are currently at, minus the distance that it takes to get to you. Okay, so this is the time when the message left. Right, and this is how long it takes to get to you. Does that make sense? Okay. This is really important in the context of causality. When you go to write the potential formalisms for V and A, you may recall that from the front of the book, this stuff, V and A. So in fact, you see here in the front of the book, V squared or V squared A and V squared V, del squared V. These two formalisms come back to that class where we talked about del inversion and gauge freedoms and stuff like that. These concepts here require us to, if you want to put our E's and D's, we can melt all these things down. But now we have a T. Let's say the particles are moving, the particles are changing. Okay. If you want to maintain causality, you have to use the retarded time. That is how long it takes for the charge to move will not be instantly communicated. Okay, and this is a very fundamental assumption, right? Because if the world was a video game where everything was known about the simulation all at once, then if me moving something over here would immediately have an effect over here. But in fact, that is not how information works in the natural world. There's a propagation time. And so we'll have to account for that in these T's. And you're going to notice something that's going to be really bothersome. Anytime that I take a derivative with respect to space now, okay, you're like, okay, that's fine. I'll just, take my derivatives as normal. But now T's have R's in it. Okay? It sucks. It makes the math horrifying. But he's responsible for every phenomenon that we use to see. Yeah.
Does that make portals break causality?
Yeah, portal's impossible. Portal's impossible, time travel impossible.
Like the.
By the end of this semester, you will not believe in time travel.
I mean, if you're talking about.
What? Can you drop the class? You're welcome to. If you came here looking for time travel, you are sorely going to be disappointed. I mean, the most interesting thing, right, is that all of the coolest, sci-fi ideas, we came up with them 100 years ago. And yet, everyone's so fucking stuck on the most banal shit. Oh, I want to time travel. Like, shut up, just come up with something cooler. We know that it's impossible 100 years ago.
Yeah, tachyons.
We can time travel.
Actions don't exist.
We can time travel in the forwards time.
I can share two things at once.
Oh no, we can time travel in the forward time.
No, we can't.
We're all time travelers.
No, we can't. Every second is a second. Yeah, I mean,
Yeah,
arrow of time.
it's
right?
1-to-1.
How is our consciousness intersecting with time? No. This is not the idea of time travel. We all know it. No multiverse. There's no multiverse. No.
If the multiverse didn't exist, you would not be able to interact with each other at all.
These are inherently non-scientific questions, right? Do you think they're scientific?
They're scientific, they can't be scientific because science means has to involve
Yeah.
proof. And since you cannot prove a multiverse, it is therefore inherently unscientific.